Hi everyone, what's up? Today I want to show you a really simple example about a line integral on a closed curve with a conservative vector field, okay? Or a vector field that is gonna give us a nice number, and you're gonna see why in a moment. So basically, the vector field I want to show you today is one you've probably encountered before, and it's a very simple one. It's going to be I'm actually not gonna use any I hat or J hat or X hat or whatever. I'm just gonna use this notation, which seems maybe more fair to people that don't know, I hat or J hat, or I know some people use I hat, other people use X hat, whatever. That's irrelevant. I will use this notation for vectors. So you've probably seen this vector before. It sort of looks this vector field before. It sort of looks something like this, and close to the origin you have tiny arrows. So this is sort of what the vector field looks like. It is basically, you could think of like a source, and as you get further away from the origin, well, you're gonna have larger arrows because the components are growing. As x and y grow, you're gonna get a bigger vector at that point. Now, I want to ask you the following: what if we have a closed curve? Let's do something. Let's pick a very simple one. Let's say we have the unit circle. Okay, that's a terrible circle, but let's just say it's the unit circle. This is just a scheme. Really doesn't have to be accurate. All right, that's a little better. Okay, this is the unit circle, and this will be our curve C. Okay, and what I'm asking you is, well, let's take a line integral over this curve. Okay, so really what we're saying is, let's do f dot dr. Okay, dr, you could think of it as a displacement vector. Okay, and f is just going to be your vector field. And there are many ways you could interpret this. You could say this is the work done along this curve by this force, if we say it's a force. Or you could also say that this shows you the circulation of this vector field along that curve. And when we say circulation, we mean, well, what portion of this vector field it goes along, what cumulative, that's important, cumulative portion of this vector field goes along this curve, okay? Remember that another way to write f dot dr is to do f dot d. Well, there are many ways to write it, but most people do this. F dot t hat times ds. And here t hat, well, you really want to see what is the dot product between f and t hat at every point throughout your coordinate system. And then you want to add that up. And, well, that sort of tells you whether the vector field is curling around the surface or not curling, whether it's following to some extent. In this case, it would curl because we have a circle, but whether f is following t hat. That's how you can think of it, okay? Now let's get into the computations, into the calculations we can do. So one way we can solve this is to parameterize a circle, and I would say let's parameterize it like this. Let's say that r, our precision vector, is going to be given, let's use an angle theta. Let's say, we have something like this, and we have a theta here. Okay, this is a theta, and we're going to have cosine theta, sine theta. Okay, because this is the unit circle, the magnitude of this will just be 1. So then we can say the following. We can say that dr, remember, dr is going to be equal to dx dy, okay? Which means that we can say that x is equal to cosine theta. So let's say down here, x equals cosine theta. That's how we parameterized it. And y equals sine theta. And then, well, if we want to find dr, we just need to calculate these differentials with respect to theta. So then we have dx is going to be minus sine theta d theta. And then dy is going to be equal to cosine theta d theta, okay? So now, our displacement vector, I'm not going to write it out. It's not really necessary. You know that you can just plug this up here. And now what about f? Well, we know f is in terms of x and y, and we know how to write x and y in terms of theta, which is our parameter. Then, well, we just get that f is going to be x that is cosine theta, and then y is going to be sine theta. Okay, so this is what we have for f, and maybe you can already see something kind of odd. F and R are exactly the same. Now, what happens if you take the dot product between two vectors that are, if you do, let's say, if you do this, like if you do A dot A, well, you know what you're gonna get. You're gonna get the magnitude of A times the magnitude of A times cosine. Now let's just say we have phi, which is gonna be the angle between the two vectors, but, well, this happens to be 1 because phi is 0. So then you have the magnitude squared. Now, well, let's see what happens if we get that, okay? Let's see. Do you think we're gonna get a number out of this? Do you think this line integral will be equal to a number? Or we're gonna get, I don't know, some sort of magnitude square? Let's see. It's pretty interesting what we get, and you'll see why in a moment. So let's actually walk through the computations. So this is going to be the line integral over our curve C, and then we're gonna have f, that is going to be cosine theta sine theta dot dr is going to be dx, which is minus sine theta, and then dy is going to be cosine theta, and these two multiplied by d theta. Okay, I just put out d theta outside. Okay, put it outside. And this is great because then we can just take this dot product and take this line integral as a normal definite integral. So then we're integrating with respect to theta. What are the bounds for theta? Because this is a closed circle. Well, this is going to be from 0 to 2 pi, okay? And then we're gonna have, well, let's see, what integral do we get? We're gonna have cosine theta, well, really minus cosine, notice this negative here, minus cosine theta sine theta plus, funny, right? We get the same thing. I'm gonna keep the same order. Cosine theta times sine theta. Okay, and now if you know a couple of things about vectors and maybe physics is helpful here. If you know a couple of things about this, you know this. Okay, first of all, this will be 0. Okay, if you've taken some math, you know that, well, the integral is going to be 0 and the integral of 0 is just 0. This is 0, which means that should I use physics? I hope you like physics because I'm gonna use physics. If this is a force and this is a curve, this is a trajectory that you have, the work done by this force on any object going through that trajectory is gonna be 0, okay, based on this. Now that is very nice and it makes a lot of sense because, okay, if you wanna see from a math perspective, well, notice that f and r are essentially the same vector, and then it follows that when you differentiate it, you're going to get something that is very similar, and you get negative. You could also then talk about conservative vector fields. You could see whether this is a conservative vector field, and then, or you could also check whether, yes, you could do that and check whether this is a gradient field also, and then you know that the line integral of a gradient field over a closed curve is going to be 0, okay? That is, why do I always think of physics? If you've taken some electricity and magnetism, you know there is an electric potential function. This is a scalar function, and basically, if the difference in electric potential will be the same along a trajectory if the trajectory ends wherever it starts, okay? Meaning it's a closed trajectory. There is no difference in the potential or the gradient. All gradient fields have potential functions, and I'm probably going off topic right now, but really, this is a conservative vector field, which is sort of like some of the fundamental forces in physics. I don't know if I've never taken quantum physics, so I can't talk about anything that's not electric, magnetic. I can't talk about anything that's not electric or gravity. Anyways, I'm going off topic. The point here is that this is to be expected, okay? If you've taken physics, let me show you this. Let's say that dr is essentially, in physics terms, is going to be the same as some non-infinitesimal displacement, okay? Let's say this is delta r. You know that work is going to be F our vector f dot dr, okay, or delta r. Now, the thing about delta r and how should I do it, you know that if you're in a circle, you're going to have your position vector and your velocity vector will be perpendicular. So this is position vector and this is velocity vector, okay? The velocity vector is going to be delta r over delta t. I'm going to use delta notation. It's going to be equal to this. Now, that means that v and delta r are parallel to each other, which means that because the direction you're traveling in, which is your velocity, the direction you're traveling in will be perpendicular to r, okay? And we know r is parallel to f, okay? Because f and r are the same. They're essentially the same vector. And that means that, well, if r is parallel to f, that means that f has the same properties as r, which means that because r is perpendicular to v, f is going to be perpendicular to v. And because f is perpendicular to v, it will also be perpendicular to delta r, which means that these two guys will be perpendicular to each other. And you know that, well, the work, if you have two forces that are perpendicular to each other, not two forces, two vectors are perpendicular to each other, their dot product is zero, okay? So this is some insights, some, a way you can look at it from physics. Yeah. There are so many things you can talk about this, gradient fields, potential functions, and there is a huge overlap with physics. It is very hard to talk about this without seeing and without like dying to talk about physics, especially if you like physics. So yes, this is very nice, and if you like physics, you're gonna love vector calculus in general, okay? So yeah, that's the entire video. Hopefully you enjoyed it, and see you in the following one.